Okay, it's 4.2, rates. We see rates everywhere. And one of the most common ways we see ratios presented as statistics. Here's some rates. Births per 1,000 people. There was 12.5 in 2008 in the United States. Birth rates per 1,000 women of childbearing age, which is different than people, right? So you'd expect it to be higher because you're taking out old people here and young people, which was 59 in 2018. And then you get all these different rates here. 820 deaths per 100,000 people in the United States, 2018, etc. Anyway, we're inundated with these rates, and they're being presented often as a single number. The second quantity in the comparison, which is what these are, has been scaled to a, quote, nice number. For example, let's look at the 1,000 women of childbearing years. 59 births per every 1,000 women of childbearing years. That's a whole lot nicer than saying there was 2.8 million births per every 63 million, whatever. It just makes it really nice, okay? So rate. A rate is just simply a ratio between two quantities with different units, with the second quantity, which is the denominator, scaled to a meaningful standard and being read using the word per. Rates have compound units, like here's some compound units. Meters per second. Why is it compound? Meters is a measurement of length. Seconds is a measurement of time. Miles per gallon. Why is that a rate? Two separate units. Miles is a measurement of distance. Gallons is a measurement of volume. So unit rates is just a rate with the second quantity has been scaled to 1. And you know this your whole life. 65 mph means 65 miles per 1 hour. Right there. So just to drive this home and to look at it, we're going to consider the statistic that there were 59 births per 1,000 U.S. women of childbearing age. We will determine how that statistic was derived, all right? Well, it was derived from this. There was 3,788,000 and some births in 2018. And in the United States, there was 64 plus million women, right? Now, it's going to be the same as 59 over 1,000, and we're going to do that problem here. This is one of the problems you should be read, right? So the ratio table, this is the ratio table here, it organizes information. So this is how they've got that 59 over 1,000. They set up their one ratio, there's the ratio, births per women, and then births per 1,000 women. So they cross-multiply, just like we did in the last section, and divide it, which is right here, and they got 59. We see we get 59 births per 1,000 women of childbearing age. So this one we're going to do together, right? Scale the second quantity to 1. In other words, they want this ratio of births per women to be births per 1 woman, right? We're just going to repeat the above procedure, making sure to use the original data and not to round it off 59. So I don't want to round off 59. I could divide this by 1,000, divide this by 1,000, and it would be rounded off. So I want you to think about how we're going to do this, and I'm going to put it down here on the paper. So why don't you hit pause and see if you can do that problem. We're trying to find X. We know that this many births, this many women, so it's what number here over 1. So if you set this problem up right, that's how you would set it up. I really should put in births on the top, women on the bottom, births on the top, women on the bottom, but I'm keeping track of it because I see the top row here is births and the bottom row is women. So you see if you can solve that, and I'll put up the answer. So there we have our answer. Hopefully you followed that, right? Cross multiply and then divide. And so the answer X, I'll put in the table. And there it is in the table. Whoops. So drag it up here a little bit. And you see we have this ratio. This is the ratio that we did, and now this ratio. Now here's kind of an interesting question. It kind of gets at to why we scale to a meaningful number, right? State the meaning in words of the rate per one in the above table. Well, the rate per one is 0.05897 births per every one woman. It's kind of not a very clear way of explaining it like this one is, 59 over 100. So to complete the table, we're going to use the idea from equivalent fractions and easily scale from 1 to 100. So I'm going to use this ratio here, and I'm going to make a new ratio with a number over 100. Now, if you recall, how do I get from 1 to 100? Well, I multiply by 100. Put that in there. And how do I get, if I multiply the denominator by 100, what am I going to multiply the numerator by? And hopefully you know that's 100 also. And if you recall from the last chapter, if you multiply a number by 100, it shifts at 2 decimals, so I get 5.897 over 100. So there it is. Here is our ratio table built up. These are all equivalent. 0.5 over 1 is the same as this over this, is the same as 59 over 1,000, is the same as these, 3 million, and really it's basically created a pair of number lines with equivalencies lined up. This example highlights an important point about ratios. There's an infinite number of possible ways to represent a given ratio. This can cause confusion. We could say, and I'll let you read that, pause it and read it. These are all the different ways we could talk about it. Notice that even though the quantity of birth is discrete, there's no fractional births like a half a birth. The rates can be use decimals, so it's allowable to use decimals in the rates. We'll pick back up here next time.